Welcome, everyone. My name is Friedhelm Victor, and together with Matteo Romiti, we're going to present to you our paper called Cross-Layer Deanonymization Methods in the Lightning Protocol. And this is joint work with Pedro Moreno Sanchez, Peter Sebastian Nordholt, Bernhard Haselhofer, and Matteo Maffei.
Yeah, welcome everyone. I'm Matteo Romiti, and we start our presentation with our motivation. There are still some users that believe that Bitcoin and the Lightning Network are providing privacy for payments, but we know that there are many privacy attacks on both layers, but there has been no work considering these two layers together when performing such attacks. And we also know that the Lightning Network is aiming at solving scalability issues, so it's probably going to see some wide adoption if successful. And lastly, we think that the Lightning Network and the Bitcoin blockchain are communicating in plain text, and this is what we are going to use throughout our work. So here is a short list of contents for the talk. And after a short background and the research questions we had, we will dive into the heuristics and the results, and finally the takeaways with the future work. So our research questions are mainly three. We wanted to understand which privacy and security issues arise from the interaction between on-chain and off-chain activity. We also want to understand to what extent can we improve our knowledge about the Bitcoin entity graph and the Lightning topology just by using publicly available data. And lastly, we want to understand how much can we link, to what extent can we link Bitcoin addresses to Lightning nodes. So short background. We start with the well-known multiple input clustering heuristic, where we use the fact that we think that the user performing a transaction controls the private keys. So in this case, we know that A1 and A2 are two addresses controlled by one entity because the private keys are controlled by one user. But at the same time, we can link A1 and A2 also to A4, thanks to the fact that the private keys are shared among these three addresses and performed by the same user. Keep in mind that during our presentation, we will have on the right-hand side a legend, so keep an eye on that to understand what we are talking about on the left-hand side. On the Lightning Network instead, we have a network of nodes, a peer-to-peer network of nodes, and here we see, for example, two nodes, N1 and N2. And these nodes come with publicly available data, so they gossip through the network their IP address or Tor address and their alias. So in this case, lnbig is the alias of N1 and IP1 is the IP address of N1. What happens on the Lightning Network is that two nodes can establish channels, and once they establish these channels, they need to write on the blockchain. So writing on the blockchain means creating a transaction. In this case, we call it funding transaction, where a set of addresses is sending coins to a multi-signature address that is locking the funds. And the channel point, which is the ID, let's say, of the channel, is referencing exactly this transaction. At this point, we do not know which node is funding the channel, so this is our first problem. Also, once the channel is closed, the coins are released from the multisig address, and they are sent to two different addresses, and in this case, we consider them as entities. So these two settlement entities are receiving the coins from the closing of the channel. Further, we can have one of these two entities reusing the coins to open another channel, so performing another transaction. And in this case, we have entity E2 that is reusing the coins from channel C1 to open another channel C2. And the same can be seen on the network side, where we have a new channel open between N2 and N3. Additionally to this, we want to say that there are two points, so the entry point and the exit point, that are made of entities and Bitcoin entities. And these two entities are simply entities that are sending coins to funding entities and entities receiving coins from settlement entities. So they do not directly interact with the Lightning Network, but they interact with funding and settlement transactions. Our data set that is publicly available online is made of 16 months of data collected using the LND client. And we performed the scribe graph command every 30 minutes. And this allowed us to collect almost 100,000 public channels and the corresponding nodes, as well as then collecting data from the blockchain, so funding and settlement transactions and entities. So the core of our work is based on linking heuristics, and we can already start understanding how the linking heuristic number one works, and we call it coin reuse, because as you can see from this graph, we have the entity Ichu that is reusing coins from channel C1 to fund and open another channel C2. Now, this heuristic says that if there is one entity receiving settlement coins from a channel and using them to fund another channel, then this entity is linked to the node that is appearing in both channels. So in this case, Ichu is linked to N2. More details and requirements are needed for this to be true, but you can find these details in our paper. One thing you should be remembering is that we do not care about multi-hop payments. So we do not care about what is happening on the peer-to-peer network. We just look at funding, settling of the channels, and what's happening on the blockchain. One other important aspect of this heuristic is that once we can link one entity, in this case Ichu, to one node in the channel, in this case N2, then we can also link the other entity, so the settlement entity E3, to the other node in the channel, so in this case N1. So if we have knowledge about one side of the channel, we can also say that the other side is linked, so E3 is linked to N1. The second linking heuristic that we call entity reuse is based on the fact that one entity has been reused to fund and open channels, and this is reflected on the Lightning Network, where one node is exactly sharing these channels. So if there is at least, if there's one entity opening at least two channels, then this entity is linked to the node that is appearing in at least two of these channels. Also, in this case, we do not care about the multi-hop payments happening on the peer-to-peer network. So any attack there is not related to this. The first results are shown here, and we can see that the entity reuse is performing better than the coin reuse. And also, by looking at the results on our data, we noticed that the coin reuse is completely contained in the entity reuse. So the entity reuse is more general. At this point, we ask ourselves, can we improve this? And to do this, we need to jump into the next section, which is about on-chain clustering heuristics. And this is added to the multi-input clustering heuristic that we saw before. So we noticed that on the entity graph, there were some patterns happening. And the first pattern that we saw is something that we call star pattern, because we found a source entity, in this case E1, that was sending coins to multiple funding entities that were then opening a channel, in this case E2, E3, and E4. The second pattern that we saw, and this is based on how Bitcoin and the change works, so the change address work, is based on a snake pattern. And we see that when an entity E1 is opening a channel, in this case C1, then the change address ending in the entity E2 is opening another channel. And if we continue this, we can see the snake pattern. And another pattern that we saw is what we call the collector pattern, where it is symmetrical to the star pattern. We have multiple settlement entities collecting the coins to destination into a destination entity. And similar to this, we have the proxy pattern, where coins are first collected on a settlement entity and then sent to a destination entity. So all these four heuristics, all these four patterns can be used for on-chain clustering. And based on the fact that these entities are controlled by the same, let's say, user, Lightning Network user, we can perform this clustering on the entity graph, on the entity level. So all the entities funding or settling these channels are actually controlled by one single user. So the next part is off-chain clustering heuristics, and for this we need Freedom again.
Thank you. So to motivate a little bit the off-chain heuristics, let me start out with LNBig. LNBig is a popular service that offered free inbound channels to anyone who wanted more connections. Now on their website, which is shown on the left here, you can see that they list multiple Lightning nodes that are controlled by them. On the right-hand side, you can see that we also asked them if a node called LNBig billing also belongs to them, which is something that they confirmed. So at the time of our data sets, 26 nodes were under their control. This is ground truth to us that there are some participants that run multiple Lightning nodes. And the idea is now to find such participants automatically. If you recall the earlier visualization, then for most Lightning nodes, we know an alias and an IP or a Tor address. If two nodes are hosted on the exact same IP, that is a strong indicator that they're controlled by the same entity. In this case, this would be for the nodes foo and bar. We've listed them here with the same IP, IP3. So nodes N5 and N3 are likely controlled by the same entity. If nodes have a similar alias, that gives us a clue, but the similarity could be by accident, and we need to specify how similar is similar enough. From an IP address, we can derive autonomous system numbers, which tells us the network operator that a certain IP belongs to. So in this case here, we can look at LNBig billing and LNBig 31. They are hosted on different IPs. Their alias is quite similar, but we can see that their autonomous system number is the same. So they're hosted with the same operator. And so now the idea is that we combine these two properties, so alias similarity and saying that they're hosted on the same autonomous system, and then we can say that they're likely controlled by the same entity. So here we've highlighted what the result would be. Nodes foo and bar would be the same entity, and LNBig billing and LNBig 31 would be also the same entity. Now, to evaluate this in more detail, we need to look at different string distance measures because we need to pick one. And there are many to choose from. One, for example, is the longest common substring. Many other popular ones are Levenshtein distance, Hamming distance, and a couple of other ones. And we also devised relative variants of these. So for example, if the longest common substring accounts for a certain portion of the longer string, say 50%. And on the right-hand side, you can see what applying the longest common substring measure would look like at a certain threshold, which is the horizontal dashed red line. What that would output if we supply it with all LNBig nodes that we've seen and some random ones. And what you can see is that it finds all of these LNBig nodes in one big cluster, but it also finds two nodes that contain the term lightning, and it finds them to be quite similar. But as it turns out later, they're hosted on two different autonomous systems, so they would not be considered a cluster. Now, as a next step, we need to evaluate these string distance measures with certain thresholds because we need to pick a threshold. Now, to do this, we impose a requirement saying a good result would need to find the Ln big cluster of 26 nodes as a single cluster. And other than that, we want to maximize the number of nodes being clustered. And you can see the result on the right-hand side. And it turns out that the relative longest common substring measure performs best in our case. And combining with the other heuristic, which says if two nodes are hosted on the exact same IP, they're controlled by the same entity. If we combine these two, then we find about 1,100 nodes clustered together in about 300 clusters. Now you might say, well, what about nodes that are hosted on Amazon? Surely there could be many of these. And interestingly, in these 301 clusters, 20 of them are fully hosted on Amazon. But they're not considered a single cluster because their naming schemes are sufficiently different. But of course, there can be some false positives here. And since there isn't much ground truth to work with, it's a little hard to quantify it exactly. Now, what we can do as a next step is we can look at what would happen if we combine the linking heuristics with on and off-chain clustering. So first, we would perform the alias and IP-based clustering, which gives us a larger input for the linking heuristics, and then finally lets us perform more clustering. So as a result, we can summarize that we can now link 46% of all Lightning nodes to 30% of the Bitcoin addresses in our dataset. In addition, we have now effectively linked IP addresses to wallet addresses. And I'm sure this is not in the interest of the user, but of course, for law enforcement, this could be quite interesting. And now we move to the validation, which Matteo is going to talk about again.
So far we saw different heuristics, and we needed a way to validate our results. We came up with this validation method that is based on two Lightning nodes running on our side. So we have two nodes, one is NS and one is NR. NS is the sending node and NR is the receiving node. And then we choose a target node that we want to validate. So NT is the target node that we already linked with our heuristics to an entity in the Bitcoin blockchain. So once we select this node, we open a channel from our sending node to the target node. And let's assume for the moment that we have 100 coins on our side. And this means that when we open the channel, we have a funding transaction on chain. And we know that the funding entity is us, belongs to us. So in this case, ES is our wallet. Next, we connect our receiving node to the Lightning Network, and we make sure we have enough inbound capacity. What happens next is we send coins from the sending node to the receiving node through the target node. So this is why you see 30 coins moving from the sending node to the receiving node. And at this point, we managed to put into the pockets of, let's say, the target node 30 coins. And we, at this point, close the channel. And when we close the channel, we will see a settlement transaction on the blockchain. And we know that we are on one side of the settlement, while the target node is on the other side of the settlement. So we know that ES prime belongs to us, while ET belongs to the target node. So at this point, we can already link ET to NT. So this gives us ground truth. Also, we can wait and see how these 30 coins are spent from ET to other possible channels. So our validation data set is limited, mainly because we had to find a trade-off between costs and also not disturbing and altering the properties of the network, but also to validate our results, so our needs. So we managed to open and close 70 channels with 73 nodes, but only 52 of them received coins from us. also, 41 of these nodes didn't spend our coins, so only 11 of these nodes actually spent our coins, so that we were able to see where the coins were going and the funding entities, the settlement entities associated to. So in total, we managed to validate 9 nodes, which means 2 nodes were not validated, but not validating in this case means that we have not enough information. Doesn't mean that is wrongly linked. More details in the paper, but this is the main takeaway. So possible countermeasures to all the heuristics we presented here are twofold. We have on one side the blockchain countermeasures, for example, using external wallets to fund channels, so partially signed Bitcoin transactions, and other well-known suggestions, so not reusing coins and addresses and avoid merging coins. On the network side, instead, just by using Tor addresses, just by using Tor, you can avoid leakage of IP addresses and also the linking between an IP address and Tor address if you use both. For the next part, again, we will have Freedom helping us.
So now we can ask for the implications of what we've shown you so far. For example, we can ask who controls how much capacity in the Lightning Network, because that's somewhat similar to a wealth distribution. Then what are potential impacts of attacks performed by single or multiple entities? What if such entities were on the receiving side of the attack, such as a denial of service? And assuming an entity has multiple nodes on payment paths, we can then study aspects like relationship anonymity and value privacy. So if a channel has been created by a user that has been linked to a node, then we can assume that the full capacity is controlled by that node. And for all other channels, we assume that each user at each end of the channel controls half of the capacity. If we sum all that up, we can look at which users are actually controlling a large capacity share. And it turns out that this LN-Big service that we've previously seen seems to control 24% of the entire Lightning Network capacity at the time of our dataset. Now, the next larger ones don't get close to this, but still have higher percentages. Overall, 80% of the capacity seems to be controlled by 10% of the nodes. One particular attack that we can look at is a grieving attack, which aims to disable parts of the network. And the way this works is that an attacker chooses a path of a following form, like shown here, where essentially the first node that is sending a transaction and the target node that is supposed to receive the transaction belong to the attacker. So essentially, the attacker is trying to send money to himself. Now, the idea is that along this payment path, the attacker tries to exhaust the capacities. So he's trying to send as much value as possible along that path, but never accepts it at the final node. This forces intermediary channels to wait to release the funds that are locked, and this timeout could be on the order of several days. Now, looking at which entities could actually pull something like this off, we can see again that LN-Big would be quite effective in doing so. If they did this, they could essentially lock down 40% of all channels and almost 15% of the total capacity. Again, there are some other nodes that don't get quite close to this, but still, for example, BFX LND is getting to something like 7 or 8% of all channels that they could lock with this attack. So then let's talk about denial of service attacks. Interestingly, in March 2018, it was reported that the Lightning Network was hit by a distributed denial of service attack that took down about 20% of the nodes. So the assumption is now, what if one of these large entities by capacity share were to be attacked by such an attack? And so to simulate this, we iteratively remove entities with high capacity shares and then check, for example, what is the size of the largest component of the Lightning Network graph. And in addition, to determine how the payment flow is impeded and the payment success, we randomly picked 10,000 node pairs to evaluate, is their payment still succeeding and how much could they actually send from one end to the other. And it turns out again that if such a denial of service attack were targeted at Alan Big, for example, then that would impede max flow quite considerably, which means how much value could actually be sent from one end to another of the network. And this goes up to almost 35%, which would be the number that is reduced by. Now, in terms of payment success, if Alan Big were taken down, then payment success would go down by about 13-14%, and the largest component in the network would shrink by about 5%. This means 5% of the nodes don't reach the majority of nodes anymore with payments. Now, finally, let's talk about value privacy and relationship anonymity. So if an entity is on a payment path, then of course it can observe the value that's being transferred through it. And we can then check on how many paths would this actually be the case for some of our top entities. Now, in addition, if an entity is the immediate successor of the sender and the immediate predecessor of the receiver, then it can determine the payment partners. And again, we can check for how many paths this would actually be the case. And so we evaluated this for all cheapest paths. So considering a certain Satoshi amount that's being sent, really check between all node pairs that we see in the network, whether their value could be observed or whether even the relationship between the payer and receiver can be seen. And again, for very large payments, this could be seen by Alan Big. So they see almost 40% of the payment values if the payment value is sufficiently large. So in this case, 1 million Satoshis. And in terms of relationship anonymity, they can see something like 15 to 17% of the payment partners if the value is sufficiently large. Now, for smaller values, this obviously decreases because you're not as much forced to go through these big players. But suppose these big players were to collude, of course, then they could learn even more. So this brings us to the takeaways of what we've shown you so far. So our heuristics are able to link Bitcoin addresses to Lightning nodes. And in fact, we've been able to link almost about 70,000 Bitcoin addresses to about 11,000 Lightning nodes. Our on-chain clustering heuristics are able to reduce almost 26,000 entities into 8,200 components. And the off-chain clustering heuristics were able to cluster about 1,200 nodes into about 300 clusters. Now, the linking attacks that we've shown you are orthogonal to multi-hop payments. We don't need information about such multi-hop payments. The linking validation method has shown that we were able to validate 9 out of 11 nodes. And it turns out that a few influential Lightning node users could be attacked, or they could band together to spy on users. And overall, our analysis has been based on 16 months of data, and overall code and data is available online. As for future work, we believe that such security and privacy analysis could be performed on other layer 2 protocols, for example, based on Ethereum, such as the Raiden network, but there are others as well. This kind of analysis could also be performed for private Lightning Network channels, and the impact of new wallet features could be studied on our linking heuristics. So this is our final slide showing the resources. So our paper is online. You can find our codes and our data sets. And with this, we close our presentation. Thank you very much for watching. And if you have any questions, please do contact us. We're happy to answer them. Thank you very much.